Greetings, gamers and sailors. Today, let me check the audio first. Yeah. Great. So today, what we're doing today, right? As you can see on the screen, we are doing buoyancy, water physics. I'm going to be working on a whale hunting game. This is for the prototype. And the first thing that we got to do is implement some simple model of buoyancy. Because that's very important for the game, because you're in a ship and you're going to be hunting whales. And the way I'm going to do it is by using Box 2D. Here I found a really nice demo which shows what I'm trying to accomplish. So basically you have this body of water, and if you drop some object into it, it's supposed to float. And when you drag it around, it's supposed to sort of, this is supposed to happen basically. There you go. So you also have a small boat which moves around. This is implemented in Box 2D. This is the Box 2D test bed made by the guy behind iForce. And the thing about this sort of model of buoyancy that he came up with is that it's actually pretty realistic. As you can see, the drag on these coins. So like the coin that was vertically aligned, it didn't get much drag, and this one slowed down due to friction in the water, and this one just spun around like this. So this is pretty accurate. What I'm going for is not this, okay, because this needs some really complex stuff. This is the article here, and it's pretty complicated because you need to, so basically the principle behind this is you find the polygon that's intersecting the water, and based on the volume of that polygon, you apply force to the centroid of that overlapping polygon. And you do this for each and every object in the water, and you calculate this every frame. That might make the game slightly slow, but what I'm more worried about is that you need to implement the Sutherland-Hodgman polygon clipping, which is pretty hefty algorithm. I mean, it can be done, but it's going to take a whole 2 days or something for me to do that. And for my use case, I don't think it matters, okay? Because there's a few parts of this which don't matter that much. And I've come up with a simplified version of it, and I'm going to implement it today. So let me just give you an overview of how this article implements it. So first step is that, and then you apply force on the object. Then we have drag, which is you calculate the movement each frame of that object, and then you apply counter force, which is opposite to that movement, and this movement has to be, this force has to be applied at the centroid of the interacting polygon, so that you get behavior like this, basically. So I'm going to grab this. You can see the centroid there. If I move this, it's going to rotate, you see? Okay, so because, it looks natural because the overlapping polygon has water particles colliding with it. Therefore, it's going to spin, okay, as I move it. In real life, so without the water, let me slow this down for a second. Without the water drag, it is moving like this, but well, let me grab something slightly different and grab it here. Okay, so so you can see it's getting slowed down in a certain direction. Anyway, we don't need this. We don't want anything realistic like that. there's this other version of drag. This does have some problems, like if you have multiple fixtures that make up a single object, it's gonna apply the force here, for example. So that's we don't need to like bother ourselves with that. And then there's this other thing which is called lift, which allows you to basically probably because of the surface tension of water and the way water particles stick together, you get a sort of, if you move this, it's not going to be lifted up, but since this boat has a slant here, it's going to sort of jump. You've seen a motorboat swim through a body of water, right? What happens is it sort of lifts up and keeps going up and down and sort of jumping. That's what we want to do, okay? If we're implementing lift, but actually we're not going to be doing that at all because we don't need this. The gist of the game is basically going to be, so I don't want the physics to be complex. I want it to be predictable, really simple, and to sort of look like the sea, basically. Just very simple buoyancy, and the actual complexity in the game is going to come from the behavior of the whales, which are going to be slightly unpredictable, mostly predictable still. And I want the player to basically, I want the whale hunting to be the focus of the game and not the water physics. So I reckon that in around 4-5 hours, I can implement a simplified model of buoyancy in Box 2D. So yeah, that's what we're gonna do today. And this one's gonna be a short stream, basically. Now let me check for a second that the stream is running well. I found. So you can see it's water, and based on the volume of that polygon, you apply force to the centroid of that overlapping polygon. And you do this for each and every, see on the screen, we are doing buoyancy. Right, the music is way too quiet. Let me try this. Yeah, it is royalty free. Okay, now let me check this. Okay, now let me check this. Yeah, it is royalty free. I think I'll configure OBS to capture a bit more of the desktop audio. Like that. Right. So, yeah. Here we go. I think the music now is pretty much configured. So let's have a go at it. Let me pop this out. No, actually, I'll do it like this. Ta-da. Okay. And yeah, so let's go. So I'm gonna start off by, let's start with the first task. Creating a Box 2D world. Oops. Yeah, that's what we're gonna do. Okay, so we're going to Whaler. For now, this is the working title of this game. Start with an empty sheet of paper, just code, right? So so what we're gonna need here is, we're not gonna be using any cameras, we're not gonna be using any, anything fancy. We'll add that stuff later, but we're gonna just be doing basically a body of water, a box, and buoyancy. That's it. So yeah, we're gonna need a box which is yeah, I'm gonna set this stuff up in well, here's what I'm gonna do. I'm just going to capture one thing that we will need definitely is the keyboard capture. So I'm just gonna open up my input stuff, and I'm just gonna use that. I'm gonna need that. Let's do these two. Okay. I'm gonna copy that to Whaler. Okay. Great. And yeah, let's make engine. Let's put that there. Okay. So this guy only has to do something like this, and that will have the input mapper, the keyboard, and oh yeah, it's not going to have the input mapper. Now it will. Okay, so this is the entire input module. All you have to know about this is that, you know, we just do KB input. It's gonna be input keyboard new, and do mouse input mouse, and we're gonna do we don't need joystick input. Okay, and input keyboard new, mouse new. Then what do we do? Right, so I need to capture all like that. And there's gonna be mouse, something with, yeah, wheel moved, there we go. Gotta do this as well. Yeah, no, I think the sea shanties don't work here, so we're just gonna have to go with our usual stuff. Great, so yeah, so this captures input. I don't think there's anything, we don't need an input mapper. That's for when you actually make the game. But now this is a tech demo for now. So here's what we're going to do. Inside of load, we actually don't need load. We're gonna do if going to do we're gonna do this, and I want to be able to spawn boxes so that they interact with each other and the thing. And we're gonna also need, well, we'll do the other stuff later. For now, this box is simply going to be not even a class. We're gonna do, this is how I do the entirety of class. This is how I implement a class, basically. So we have a new, well, it is going to be a primitive class, so I kind of lied when I said it wasn't going to be. Anyway, so this is how I implement this. I do, yeah, so we pass it an object. It has a bunch of defaults here, and we make a new instance. It's gonna be O or that. Then set meta table instance self, and self index is self. And that's it. Something like this, right? So we'll do, let's make it 50 by 50. I have a physics module from my old games. So I'm just going to copy this to this is a mix-in, actually. So yeah, it's a weird mix-in, actually. The way we draw this is going to be, I think I also have another, yeah, this thing. I think I'll just delete this, go into main, and I'll just drop this in here. Or actually, I'll just drop this in acquire util or globals. We'll do globals. There we go. I'm gonna do, I should really have like a single folder where I have all of these things all together neatly arranged, so that I don't have to waste 30 minutes every time I make a new project. Yeah, I should do this actually. So I'm gonna do Euler. I'm gonna copy this into Euler. Actually, I'm going to delete this first. Then I'm going to make src and move these things into src and make a readme. Oops. Readme. Boiling game. Okay. Next we're gonna do, I'm just gonna copy this into Euler src. Then I'm going to, basically we're not gonna be needing this. Yeah. I'm just gonna do require, oh, does the engine turn input? Oh, it does these separately, which I welcome. I welcome that. So we're just gonna do something like this. So require engine init. Okay, and keyboard input new, mouse input new. And what we need is a physics mixin. I'm gonna add that here. The state machine should also be sort of called a mixin, something like mix physics, or something like that. Okay. So the way it should be named is if it has global methods, or if it's a self-contained, just a module of methods, it should be lowercase. Okay, like inspect, like UUID, like LFS. Okay. If it's a mixin, it should be mix state machine, mix physics. And if it's an object, as in like if it's class, then it should just be capitalized with underscores. Yeah. So these two are gonna have to be renamed. But for now, mixins have the same format as methods or just function packages, whatever. So let's do physics. Yeah, this is okay. This looks okay so far. Right. So clear, and then for each object in objects we do like that. Then we draw the print get info string at 0, 0. Let's do it there. 5, 5 actually. So we're also going to get the well, we're going to do font is how do we get the terminal has that. Oh, I forgot to actually initialize the repository. Yeah, I'm gonna add all that stuff. Okay. Now we're gonna do terminal. This has a way of grabbing the font. Yeah, something like that. So I'm gonna do debug font size. What is that gonna be? Let's do 16 mono. Okay, so here we set the font and then set color to be white. And then we print the info string, which is gonna be this is gonna print some information at the top left corner. We're gonna do object count FPS. That's it. Okay. String join actually. Love timer get FPS. And I'm gonna do objects equals that's it really. Okay. And we're gonna update all the objects as well. Capture the input, handle the input, then we do a for loop. Okay. Let me just try and run this. Now we're getting somewhere. Expected, yeah. ENG physics not found. Yeah, we don't need this. Physics. Yeah. join. Oh yeah, we gotta make changes to the engine, which has to add a bunch of stuff. So basically I'm copying this stuff over to here. So it's gonna be Whaler, RC engine. Yeah, sure. Okay, so when we init, we're gonna do require engine math cable string. What else is there? Yeah, nothing else. Okay. We should do no, didn't mean to do that. Yeah. We should do print. Okay. And I'm gonna move this stuff into print. Okay, awesome. So we got this. Yeah. Now we're gonna do. I'm just gonna spawn a box. Before that, I'm just gonna grab some water. Be right back. back. We're back. Sailors and gamers. We're back. We're back, no one. Hello there, no one. I'm talking to myself. No, I'm just archiving this. Right. So we got this, and now we want a box. Whaler, of course. Right. So we got the engine. Just to use stuff from the engine, you just do boop, and then you get everything. Okay. Yeah. Now we're gonna. Maybe I should have something like this in there. Anyway, so good stuff. So this is the entire source file so far. That gives us this. Very nice. Now we're gonna implement the box. Yeah. Okay. So that's that. Actually, if we... Ooh, I know. So when we have engine physics, what this does is it takes GameState.world and adds it to the world, basically. And what we want, it's something slightly different. We should have. Well, let's make a world. It's gonna be box 2D world. We'll do box 2D world. Love physics new world. And when we define a new world, I should really have a link like this. Physics new world. Should have this open at all times, basically. X component gravity, Y component gravity. Right. Let's do X is going to be 0, Y component is going to be 9.81. And sleep, what do you mean sleep? What's a sleep? Sure. What the hell? You can snooze. Yeah. That looks about right. There are some things that my physics wrapper does not implement. There are lots of things it does not implement. I remember there was some kind of set meter or something. Yeah, meter scale factor. So 30 pixels per meter. Sounds about okay, you know. So yeah, we create a new world, and we should do the physics. Not sure. Maybe we should make a new fixture which has the world argument in it, because this is not going to be changing. So physics, let's see. Or should I have some sort of collider which which just contains all these things and has just a user data set as the parent? Right now it doesn't matter. I think it doesn't matter at all. And just these things being spread out into the object, it's also okay. It doesn't matter whatsoever. Do world. Pass that in. Oh, oops, my bad. This will have to. Yeah. Do world here, and we'll do. Nope, like that. So now we make a box. Yeah. We'll use the global. And we'll do, then let's spawn a box. Okay, so let's spawn one box for now. So we'll do table insert. Okay, so if we run this, my bad. We should do a graphics thing here. Okay. Let's see, physics lower 24. Object type. We don't need that. Okay. Right. Border color. So it's gonna be this, but darker. So we'll do. We'll just lower this by, I don't know, 50. Yeah. Something like that. RGB. Oh yeah, I have this. Yeah. So let's do. So it's basically just gonna be this, except color. I'm not gonna be setting any color. Color. No color. Awesome. I think they should be something like that. Okay, so now we need to go here and update the world. So we get all the inputs, apply all the inputs, then we update the world. This box will fall down really slowly. Why does it fall down so slowly? I don't know. This force is in newtons, right? Gee, I'm not sure. Let's see. Why is it moving so slowly? It's probably because I have linear damping, just, you know, set at a crazy high number. Yeah, so it's 1. It should probably be something like 0.1 or something. Let's see. Returns a body. And we'll do. No, not get linear damping set. Damn it. Yeah, it is floaty right now. What is the default linear damping? Oh, look at that. Huh. We'll do... is it set meter? Yeah, okay. Let's do 30. What is the box size? It's 50. Let's do 50 then. Okay, let's do linear damping set to 0.1. Great. So now I want another box, which is static. Yeah. So we'll make this is the crate. This is gonna be the floor, and then we're gonna make water. I'll do 0 on Y. We're back, sailors. Okay. Get height. Let's do 150. Should be good. Yeah. Okay. Let's hope this works. Oh yeah. Oh, it's also falling. Yeah. Collider type static. Also, here's what I'm gonna do. Actually, we'll do game width. Game height. Yeah. So game width divided by 2. Game height. Yeah. And then game. Right. No bounciness. It should have some bounciness. And let's apply angular force on it. Box. Three newtons. My bad. What is the angular damping according to the physics? Oh, the rotation is locked. Okay. Set fixed rotation. Yeah. There we go. So. Okay. Bounciness, bouncy. Restitution, something like that. We'll do maybe the fixture has restitution. Fixture. So 0.2 by default. Nice. If it's a crate, I want it to sort of, yeah, let's make it bouncy. Let's make it a little bit bouncy. It's pretty good. So now we have a box that falls down. That's great. Next, we want to make body of water. Body of water. Like that. So. Add box and floor. Okay. Oh, I gotta set up a git remote origin Whaler. Upstream, right? So let's make a new repository, shall we? New repo. All right, Whaler. Boom. Okay, perfect. So, what I want to do is be able to drag the object around using my mouse. Kind of like in the test bed here. I want to implement this. Okay. Yeah. These objects are a bit too floaty in the test bed. Yo, what is this? Cool, anyway. You can play with this stuff all day. By the way, this is the lifting, so you see the motorboat sort of jumping up and down. That's what it means to apply lift, basically. Look at this trick. Anyway. So I want to be able to drag the object around. So here's what we're going to do. We're going to take the mouse, not going to do any transformations, not going to do any camera stuff. We're just going to... one way to do this is... to create a circle shape for the cursor. When it's right-clicked, we teleport it there, collide it with the object, and then get the coordinates of the collision, and then get that exact point on the box. And until the mouse is released, all the change in the mouse's coordinates are used to apply force to the box. Okay, so let's do that. I'm gonna make a new so if mouse input state buttons, left mouse button, is down, then we're going to do grabber, how about we do the visual stuff first, then we do the other stuff. Okay, so when we press the button, we want to draw something. Okay, so if it's down, then we update the cursor grabber, and we're going to make cursor, let's just update the cursor. Why the hell not? Okay, there we go. So, and we're going to do okay. So self x equals think I'm just gonna copy my old collision manager like that. So the way this works is when the cursor comes in collision with the default, so any object, which is like a box or a ship or whatever, then we run this function. When the collision is exit, then we run this function, right? So it's a direct mapping, right? So cursor in contact with default. Water in contact with default. Well, exits in this case. And these two magical functions are what do that, mixing and matching. So when the cursor enters into a box, this is what we do. We mark the box as currently selected for the cursor, and the cursor saves the contact position and remembers that point on the box and just applies, starts applying force. Yeah, okay, so this is what we do. When we click on it, we save the object. When we unclick, we remove the object. Okay, so cursor track. Start dragging, and we'll do cursor stop dragging. Okay. This will have drag objects. Objects currently being manipulated by the cursor. And local xy. I'm gonna print number of objects this thing is dragging. Okay, so drag objects, sorry. Yeah. And we'll just do a function. A function. That is, okay, start dragging and stop dragging. We'll do a linear search. So if table find drag objects then return end. Well, if not table find, then we insert drag objects and when we stop dragging, we do if table find self drag objects then we table remove. Well, look, let's do, what does table find return? This is my method. Lua doesn't have a find. So let's see, returns the key, otherwise returns a nil. Right, so we're gonna do this and key. Boom. All right. Yeah. 1, 0. Why is it wiggling up and down? Oh, because gravity. Because gravity. It's trying to fall down. How do we not apply gravity to it? there. Yeah. This guy has a custom gravity. I've never actually done that kind of gravity, or it's 0 or something. Oh, so this guy does. What? I don't want to do that. Boom, there we go. Set gravity scale on the body. Yep. Physics. Great, so it's not, no it's not. No, it is. Oh. My bad. I'll do a larger, 0. Oh. Yep, no it's not jiggling and wiggling. Let's make that bigger and I'll do fill. So we're not grabbing anything, we're grabbing one object. Yeah, it makes sense because that's the only, yeah. Yeah, okay, good, that works. So now, let's drag it. Let's actually drag it. So we'll do apply force to all dragging grab objects. Okay, so for obj in self drag objects. So obj body. Apply linear impulse, and we're gonna have to do object body get position. This will give us the center. We'll be dragging the center around for now. So x, y is self body get position. Yeah, we'll do it like this, so we don't call that function each time in the loop. Then we do bx minus x and by minus y. Simple vector stuff. Yeah, the other way around actually. Yeah. Okay, so when do we stop dragging? Okay, collision manager. When we let go, basically. So we don't when we don't do that. We'll do stop dragging everything when we let go. Okay, so set active false. Self drag objects is this. So we don't need that. So, this is crazy. Does this thing not have any damping? So yeah, this just adds. So this is how you can implement motion of the stars, but we need to normalize this vector, and yeah, that's all we need to do. So we'll make a new vector here. That will have that. Then we'll do okay, so here we will set v set xy. Then we'll do subtract vxby, normalize, and we'll do vx dy. Boom. Oh, like that. So yeah, so that's good. That's good. But we need to do scalar molt, and we'll do self-drag force, and I'll just drag force, set this at like 10 or something. My bad. Bloop. Yeah, too weak. Way too weak. Oh, way too strong. Maybe what I think we should do is multiply it by the mass. I know, crazy concept. That's kind of crazy, bro. Why would you? Yeah, because we want to be able to drag and do all sorts of nasty things to these objects, regardless of their mass. Because if something is heavy and I'm dragging my mouse across the entire screen, it's gonna very slowly start shifting. But I wanted to affect every single object the same way. So we'll do this and do obj body get mass multiplied by the mass. Okay, that's too weak. We'll do 40. Yeah. Ah, that's kind of rad, to be honest. Yeah, it is applying the... Well... Yeah, we need better linear damping, higher linear damping. Gravity force, I would say that's pretty good. Let's do... Well, if it's closer, I want to apply less force on it. Also, I don't want to apply linear... Yeah, let's apply a linear impulse. That's better. Yeah, that's what we do. But, honestly, I'm okay with this, you know. Okay, so... Yeah, we gotta add the... We gotta increase the linear damping to be like 0.5 or something. Yeah, it takes a billion seconds until it... Angular damping. I mean, yeah, that looks pretty good. Let's do this. We'll get the distance, okay, and we'll do the length, something like this. I don't have a length function? Heh. Wow. Can you, oh, I have, yeah, I'm done. If dist is more than 1, then we normalize, and we'll do something like this. Otherwise, we do v-scalar mult and call it a day. Okay, let's squeeze all these fellas together. Like that. Okay. Alright, so the... It's bigger than 10, I'll normalize it. Actually... Yeah, this is good enough, I would say. Yeah, we don't need some super robust solution for this. Okay. Okay, so now let's add the water. We'll do... there. Let's do the water. So this is gonna be Let's make the lower half water. Okay. Let's make it 400. 500, whatever. No. Let's do actually the 400 and do collider with this. Actually half, yeah. And we'll spawn it there. Okay, so height is gonna be 400. Well, that is already true for water. Yeah. For water, we want blue color, bluish. Yep, that's pretty much what I'm looking for. So 43 and 24. 168. Yeah. Three. 184. 208. Yeah. We'll do. And then we'll also do collider sensor true. This is what was causing. I'm so dumb. Oh my goodness. Yeah, let's reduce this back down. Water, right. Yeah, I'm gonna do, let's see, water. Yeah, pretty much the same stuff. Okay. Yeah, so let's do box and apply. Oh, I wanted to. Yeah. Can we get the point? Right, let's do point dragging. Okay. Body. There we go. When we start dragging, we'll do... is this X position global? Yeah, I guess so, yeah. Yeah, so we'll do... apply linear impulse. Put that much. Let's do applied force. Yeah, that's way too weak. Okay, this is better. Except we'll do 1,000 here, maybe. No, 3,000. Okay. And here we will add X and Y. Let's take a calmer playlist. Part of force not directed towards the center of mass will cause the body to spin. It depends on the rotational inertia. Force components and position must be given in world coordinates. I am. Same here. It's acting on the center of the body, it seems. Should be able to rotate this thing. Unless angular damping. Come on, you. Why can't I rotate it? So when we collide with it, what does the oh no, not that. Yeah. I think what he does is he creates a joint between the mouse and the object. Then he destroys the joint the moment it's gone. And this joint is attached between the cursor and the point on the object. And it's not a weld joint. It is a revolute joint. Distance joint basically makes sure that the distance between the two objects is constant. Then we have no, we don't need that. Relative motion between them. This is also not what I'm looking for. You can apply torque to this joint. Yeah. Oh, this is nice. This is exactly what I'm looking for. Let me try this example. Does it rotate this stuff though? Let me check. But this, yeah, no, this welds the center of a body. That's not what I want. I'm not looking for that. Yeah, I know this one. We don't need that. We don't need a prismatic joint. Yeah, so a revolute joint is what I'm looking for. Maybe a wheel. And we don't need to restrict it to a line. So basically a revolute joint is what we're looking for. Revolute joint between let's see. Oh, it's not grabbing it once it falls down. Yeah, it is. What the hell? Come on, man. Ha! That's a bug that we need to fix. Let me just yeah, so now it's what's up, CG? So when I click something else, it screws up. Okay. No. The collider is active, but I have no idea why this is happening. So drag objects. Let's do this here. Collision manager. Let's see. Let's do. Okay. Aha, it's not colliding anymore. Why is that? Maybe the box is falling asleep. So let's disable sleeping. Okay. Ha! So it was. Frickin' box duty. So the box was falling asleep because the simulation decided, oh, we don't actually need anything here. Why does it jump when I click? That's so weird. Oh, I think I know why. When I move the window, it freaking jumps. That's so ridiculous. If I keep holding it for a really long time, it's gonna jump further. I know why that is happening. It's because the game is halted when I'm holding it, and there's a small collision still going on, and since it was halted for a really long time, Box Duty decides, oh, we gotta compensate, and it just applies a higher force. So yeah, whatever. Doesn't matter. For this demo, it does not matter. Okay. So, now we can drag the object. I want to be able to rotate it with this dragging motion. I don't want it to apply the thing to the center. So here's what we gotta do. When we start dragging, we create a joint. Then we have to attach that joint to the body of the object. And we gotta stop, no, sorry, so like, this needs to be here. And we need these drag objects to have, yeah, basically this is what we're gonna do. It's gonna have a joint in there, and that joint is gonna be a revolute joint, and it's gonna be attached to the mouse. Okay, so let's do a quick thing here. We'll call it physics. So new revolute joint. let's look at what the revolute joint needs. So body 1, body 2, x, y, and in this case it's gonna be false. Okay. So self body, object body, we need position and false. All right, so this is gonna create a joint. Then we're gonna pretty much that. And we're gonna do should we have a separate array for this? For the joints. Okay, how about like this? Count. So I'll do and we'll do something like self drag objects self okay obj, then if not then we create one and we're gonna set that object to be joint obj. Let's save the position as well. Initial x. Okay. That's what we're gonna do. And this is gonna be like that. Oops, sorry. And we're gonna actually do this like that. Okay, so this guy is gonna do drag count, right? And then stop dragging the object. So we'll do if self drag objects has the object. Okay, and then we'll do self drag objects at index object nil, and -1 to the drag count. And here we'll iterate for each key and then drag in pairs self drag objects. The key is actually the object itself. And this is the drag instance, I guess. We'll do we need something like this actually. Like that. So now, if we do, crap, my bad. So, we gotta schedule this to happen next frame, okay? Tres wagethep Actually, let me do this. Lake, water, and add buoyancy. What? ვაკეთებთ ფიზიკის სიმულაციას ახალი თამაშის პროტოტიპისთვის. Right. So we can't create objects while inside of a collision callback. So we have to schedule the creation of this stuff. So I'll make a simple array and do this. And when we gotta stop dragging, we'll do okay. When we're updating, if for function in pairs self schedule do function, yeah. And then we do so if self schedule then it's more than 0. Self schedule is that. Oops. Boom. Yes. Haha. Okay, it's kind of working. So the joint is working. Pretty good. Set position self. Right. We don't need to apply any drag force anymore. We're kind of holding it, kind of. Just barely. It's really heavy, I guess. Okay, so we'll do why isn't drag count increasing though? Oh, also, collider mass has to be like 1,000 or something. Yes! Oh. That's not good. Okay, this is not good, but we are close. We gotta destroy the joint, right? So, self-drag objects, obj.joint. How do we destroy a joint? Destroy. Right, we'll do destroy. Okay. Yes. Aha! So now I can throw this box around. Yes. Fuck yeah. Woo. Let me balance this. Let me try this. Hold on. Hold on. 1 sec. I gotta whip it. I gotta really... Oh. Check it out. Oh. Okay, anyway. So that's that. Add a dragon with a mouse. Okay. So we have this. Now let's add buoyancy to the water. The way we add buoyancy, that's kind of hard. So as towards the beginning of the stream, we're gonna go over buoyancy again. So I described a model of buoyancy which works with Box 2D, which is basically you have a thing and you have water, and what you do is you calculate using some extreme Sutherland-Hodgman polygon clipping. You calculate the intersection of those two polygons, and you'll have this third one, and then you calculate the volume of the polygon that is inside the fluid, and you apply an upward force which is proportional to the volume, okay? And you apply the force at the centroid of the polygon. Now this is, the only complicated thing about this is the most important thing about it, which is to find the intersection. And I'm not going to do that because that will take probably at least like 10 hours or something. And also, this game doesn't need this much complexity. It doesn't need this realistic simulation of water. So I've come up with an alternative version, which is basically to just use the center of the polygon and apply force to it. If it is apply force to it. Depending on how close it is to the edge of the water. If it's in full collision, then we apply the full force, and the farther it is from the edge, the smaller force we apply. If it's not in collision, we don't apply the force at all. Okay, so the way to do this is when something goes into contact with water, we keep an array, and all the contacts that the water has, it one by one applies force to those contacts. So right now we're basically just going to implement a gravity field for all the things that are in the water. So we'll do collisions, active collisions, I guess, and we'll do for each. These active collisions are gonna have bodies, right? Let me see. Collision manager. Oh, I passed the objects themselves, right? So I'll do colliding objects. Something like that. Okay. Pairs colliding objects and we're just gonna apply. We'll do density. Which is what is water density? 1 gram per cubic. Yeah, of course, everything else is based on water's density. The exact density is this. Yeah, so no, the density of this thing is 1, basically. And so I'm going to be applying force depending on the density of the object. Okay. So I'll spawn 3 boxes, all 3 with different densities, and it's gonna react differently. If it's more dense, it should float up very slowly. If it's denser than water, it should just sink, basically. So let's spawn more boxes. So when we're loading, oh, by the way, I wanna test something here. Before we do this, I wanna test if the reset works. Yeah, it works. Perfect. Okay. So, oh yeah, cursor. Let me set this to somewhere there. Or let's do something like that. Yeah. Let's not draw the thing at all, right? So we'll do self body set active false. Okay, great. So we have the reset working. Node spawn. Thank you. Yes, it is interesting. Okay, so we're gonna spawn a second crate. I'll do denser crate. And I don't have density in this thing, so we'll do, let's see, density, no, how about fixture? Set the density of the fixture. Kilograms per square meter, right. So reset mass data, right. Yeah, I can just set the mass and the density will basically be determined based on that. Let me try something here. What is the mass of this thing? Let's spawn this at 100. And we'll do collider mass, I don't know, 100 kilos. Okay. What's up? There we go. Oh, come on. There we go. Why is that? Okay, let me do something here. Box print mass. So we have love graphics printf. I'm gonna print the mass and the density on these things. Okay, so I'm gonna do F awesome, that's really great. So we're going to print the mass in the center of the box. So this is going to be, I'm going to get the position of the box, self body get position, and I'm going to print this at the x and y coordinate. Limit is going to be self collider width, and align is going to be center. Align mode, let's do center. Yes, perfect. And I'm also going to print it's going to be self body get mass, so that many kilograms, and this is going to be that many. Oh, let me just check if my printf is correct. 100.00 kilograms. Okay. Let's do %IKG. Okay. Great. How about justify? What's that gonna do? Okay. This is going to be self body get density, or maybe, yeah, self fixture get density. And this is kilogram per square meter. Cancel. Let me see. Let's not do float. Why is this not drawing in the center, though? Center. Okay. Okay, I guess. So this is the string. This is the x coordinate. This is the y coordinate. Okay, 1 kilogram, 100 kilograms, and we will do density now. So this is density. Okay, good stuff. Let's add a new line and boom. Except this is like kilogram square meter is way too small. Okay, let's do double. Okay, this looks pretty good now. So, no, this density cannot be the same. Oh, box 2D doesn't, yeah. So it doesn't calculate volume, and it doesn't calculate density based on the volume. You just give it the density, okay? So yeah, what we need is to set the density correctly. Okay, so we'll do in our physics thing here, we'll do calculator density, let's see, mass, okay. If obj and we will do reset mass data. Okay, and here we will do density 3. Okay. That also changes the mass. Okay, so let's do 30 kilogram and 1 kilogram. Oh, look, this is also a box, so it's printed the data on this guy. Okay. Next, okay, what we want is let's see. What if I don't do this? Quick question, what if I don't do this? Ah, it does not adjust the mass. That's interesting. Do we want it to adjust the mass? Yeah, sure, why not? Yeah. Okay, anyway, so that's that. Now we add an upward force to all the objects inside the water. So water. Let's see. So object dot body. If object body, then object body apply linear. No, apply force would be better. Yeah, force upwards, which is 0, minus 10, so minus 20. So this is the density of the water. Let me actually also do this here, so that we have the density of the water as well. So let me try this. Okay, we have the density of the water. Why is it 0 kilograms? I don't know. Let's do 1. Oh, because it's static. Yeah, okay. So next, we'll do. Let's just apply a flat force. There's Archimedes' equation, which says Archimedes' principle, buoyancy. Equal to the weight of the fluid displaced by the body. I learned something different. Usually, in games, you don't want super accurate simulations. Most of the time, the old physics are the ones which are most useful because they're simple at the macro scale, easy to implement, easy to understand, and they're actually faster than really detailed simulations. So Newton, Archimedes, and Galileo, all these old thinkers who made theories which were very simple regarding the macro world. Their theories are actually what are most useful in physics-based games. Yeah, right. So this is the formula. No, this is not the formula. I can use the formula as follows. Apparent immersed weight equals weight minus weight of displaced fluid. That makes sense, right? And expanded by the mutual volume. Density of the object divided by density of the fluid equals that. So no, we don't need to integrate anything. So the volume of the displaced fluid times the gravity times the density, if that is equal to the mass times gravity. So in this case, well, this is mass, basically the same thing. The density and the volume multiplied. This is obvious. Right, so if it's so it's gonna float in this case, I guess. No, it's not gonna float in this case. It's gonna remain in the same position in this case. What is the force that we need to apply? Right, so basically because it is proportional to the fluid density, if an object is really dense, it's going to sink, okay? If it's not dense, it's going to float up. Therefore, whatever formula we have, the density of the object needs to be up top, and that needs to be probably divided by the water density, because if the object density is higher, no, actually the other way around. Yeah, so the force applied on the object must be counter-proportional to its density, right? Because if it's really dense, it sinks, so the force that's applied on it is low. Not because the force applied on it is slow, but in our simulation, we're not going to apply a strong force. We're going to simulate it, right? So higher density means lower force. So in this case, in actuality, we would have, oops, I'm going to just simplify my life here. Let's go. Let me get a brush. Boom. Okay. So, if we have a square and a body of water, the force applied on it, which is going to be F, we have the density of the object. And this needs to be basically, let me add this, okay. So, so the density of the water divided by the density of the object, this needs to be multiplied by maybe some kind of multiplier. Let's call it W, the water force or whatever. And we can configure this, okay? depending on if we want the water to be more coarse or whatever. I mean, we could actually configure the density of the water itself, so that we could just get rid of this. Because the density of the water doesn't matter in any other formula, so we can directly modify this. So the force that we apply on this is going to be that, basically. Is there anything else to consider? I don't think so. Because this density, basically density decides mass in our case. So we know the volume times density is equal to mass, right? If volume is square meters, and this is mass over the volume. Yeah, that's correct. Yeah, okay. So this, basically this decides the mass. And volume is already decided. Volume doesn't matter in this case. We decide this thing, and then that decides the mass. And so no other, basically nothing else needs to be considered here. If we need a more detailed simulation, I will maybe consider other things about the object. And I have other versions, right? So let's just divide the densities and do it like that. So we've got the density of this guy, this water, and we're going to be applying a force which is minus self-fixture. Well, let's do collider density, and this divided by the density of that thing. Okay, let's do object density equals object body, object fixture, and object fixture. Get density. Actually, I can just do this here. Yeah, whatever. So self-collider density divided by that. This is going to be force, and we'll apply minus force because we want it to go up. Yeah, that's nice. So after start colliding with object, self-colliding objects, table insert. Actually, if self-colliding objects table find, if not found, then we add it, and water stop colliding, and we'll do the same thing. So we'll do local So if IDX, then table remove from that the index. Okay. Good stuff, good stuff. So now collision manager has to, when we enter the callback, when a collision enter event happens between water and anything else, in the boxes basically, we'll do water start colliding with default. And when the collision exits, we do stop colliding. Oh boy, let's try it. Insert wrong. Yeah, my bad. And here we need to find the object. Yeah, I missed out. Cool. Let's print colliding objects. We'll do Let's do it. Where should we print this? Let's do it in the center. Yeah. That's not really the center. Oh, one sec. Let's get some music. Okay, so printf. Yeah. Okay, so it is colliding with 2. Now it's 1, 2, 1, 2, 1, 2, 1, 2, 2, 2, 2, 2. Alright, great. So now we've realized that the force is not enough. So our formula here, 1 divided by some 100 or something. Let's make water density higher. Okay, so let me try something here. I'm gonna extend the water to be, so I'm gonna do something like this, main Lua. So we will have a crate in water, falls in water. So we'll do this. Then we'll do crate falls on the floor. This is going to be basically the same crate, but slightly to the right. We'll do 600? No. Yeah, let's do 600, right. The water, actually, I want it to be times 0.8, something like this. Let me try this. Okay, great. So now we have a comparison. You see, the water is actually doing something. Look at this. So these are 2 exact same boxes, and one of them is falling sooner than the other one, which I think is awesome. Okay, so now we'll do 1,000. Yo, look at that! It's floating on water. That's incredible. Although one thing is, you know, it's way too bouncy, obviously. This 30 kilogram thing is way too heavy, okay? So we'll do, maybe we'll change the density of these things. This is dense crate. We'll spawn this at 80. Yeah, density is 30 kilograms per square meter, which is, yeah, not super dense, but whatever. Actually, this should be like 10 times bigger. That's funny, that's really funny. Yeah. I want the dense crate to be like 10 kilograms or something. Okay, and water density, let's make that 500. These do not reflect like real. Huh? Look at that. It's floating up. It's floating back up. Let's do water density at 800. I want the default crate to just float. Alright, so we'll do linear damping. We'll do higher, yeah. Okay, so we'll do dense crate. Let's do 3. And we'll do light crate. So this is collider density is going to be 1. Okay. We're gonna do light crate. Okay. And this density of this thing is going to be 1. Let's do 0.5. That's 1, and this is 2. Okay. And the so dense, normal, light, and then whatever. Okay. So we'll do dense on the left. Normal at 200, and then light at, okay, let's do this like this. Dense crate first, then normal crate, and then we'll do light crate. And then we'll do normal crate, dense crate and water. Yeah. All of these fall in the water except this one falls on the floor. Okay. Let's do 1, and for this we'll do 1.5. Okay, and okay, go to the box, and when we print this stuff, we'll do G. Okay. Let's do water density. Let's do 500. No, actually, wait, this should be 1,000. Is this not gonna float? No, okay. Let's do 1,200 then. Awesome. So let me just do this. Oh yeah, it's not applying any weird force. Okay, so I like this. This is pretty good. Except angular damping needs to be... Oh, does the box fall correctly? Okay, physics. Angular damping needs to be much higher. No, that's way too high. Yeah, that's pretty good. Linear damping, let's do 0.9. Okay, so add water and buoyancy. I'm gonna say the task is complete. Now we have to, so basically I wanted to test out that. Now we gotta do one thing. So apply less force to objects, basically apply force proportional to the size of the collision, basically. So, yeah. The text needs to be edited, I guess. Okay. So yeah, what we need to be doing is, so right now here's the issue. Okay, let me show you the issue. So this guy works perfectly. Oh, actually, does it fall down more slowly? Yeah, absolutely. Okay, so this is dense, therefore it sinks. This is kind of dense, therefore it sort of floats. And this guy is super light, and therefore it does not float. So, something like that. Here's what I want. I want this to be 3, I want this to be 2, I want this to be 1 again, okay? So the water needs to be adjusted. Let's do 15, let's do 2000 for now. And, close. Okay, so 1800. No, actually 2000 is correct. And normal crate has to be, so dense crate will have to be 3, normal crate 2, light crate 1. Okay, something like this. Yeah, so 3 kilograms, 2 kilograms, 1 kilogram. So this is slowly rising above the surface of the water, really slowly. And then it sort of floats. So what I want, so I don't want this to happen. That's one problem, which is it just keeps jumping up and down, okay? Second one is objects don't float like this in water. They sink a little bit and they stay there. This is because the force that the water applies on the object is proportional to how much it is submerged in the object. So how, and we're going to calculate that. But right now we are just, if it's colliding, we are applying force. So that's why it has to leave the water completely for it to stop receiving force. And then it starts going back and forth. This is not natural. So what I think we have to do is apply force proportional to how much it is in water. And we can calculate that using, this, or my simpler solution, which basically just takes the center of the object and compares the distance of that object to the closest edge of the water. Yeah. Now the tricky part here would be, how do we find the closest edge of the water? Well, the thing is, my water, I know for a fact that my water will always be rectangular. That's one thing. I know for a fact that I'm not going to have like vertical columns of water. I'm not going to be like making water which just ends abruptly so that I can do some weird, fantasy physics. I know the water is always going to be on the bottom, and I know it's always going to be a rectangle. So what I can do is basically calculate not even the closest line on the water, just take the top line and get the y-coordinate of that top line, and then I measure the distance, and if it's close to that top line, well, if it's colliding, if the object is colliding and its center is lower than that, then we apply well, the logic will fall into place, but basically I'm gonna be taking the center point, comparing it to this point in y-coordinates, and if this is bigger, so if the basically if the box is here, then we apply, let's say, like a force of 9. If the box is here, then we apply a force of like 3. And this is depending on how close the center is to this line here. And if it's below, then we add more. If it's above, then we don't add more. Yeah, that's what we're gonna do. So we're taking some liberties here with how the water is gonna work in the game. So let's do water. I'll calculate, so self water line y is going to be self body get position local x and y, and this is the center, that minus self collider height divided by 2. Yeah. And then when I'm updating, the force that I'm applying on these fellows will have to be modified by, okay, so set force to how far the center of that object is from this water line. So we're going to have to get object x and object y. Then I'm going to do object y. Actually, we don't need this here. If object y is more than self water line y, then the force that we apply well, if it's okay, how about this? If it's less than that, this means it's higher. Then we reduce the force depending on sort of the distance. Okay. this is the distance. Well, actually, this is going to be the distance. And this will have to be divided by the collider height. So I think that's not super correct, but we'll try. Yeah, that is weird. Yeah, anyway. It's less than waterline Y. Then the force that we apply has to be less. Okay, so if the object is right at the middle, so if it's less than that, then this is the distance above the water. Well, what we need to do is find how much it is submerged into water. So distance below the water. Okay, so we'll do local below water volume. This is going to be object collider height. And actually, yeah, we're basically going to be simulating this, but the actual formula here is the volume squared or something. Density of the fluid and the volume, right? So the volume below water multiplies it, right? So we'll do object collider width, except collider height is not actual. Yeah, so we'll do how much it is submerged. So we'll do the top side minus the water line. That will give us how much it's not submerged, and we'll, yeah, well, actually the bottom line compared to the water line. Yeah, that would give us a reasonable thing, but I want to do it from the center. Because I want it to be a bit more general. Let's do it. Let's do the easiest version, which is the lower side. So we'll do local OL is going to be y plus obj collider height divided by 2. And then self-water line y. No, the other way around, right? So OL minus, this will always be higher than waterline Y. This is the height. So now this times obj collider width times obj, well, we don't need to do that. Okay, so this is volume underwater. And this will have to be this times volume underwater. Oh my god, that is not accurate at all. Let me actually do something here. Okay, so this is reasonable. Let's do let's only do this for the dense grid for now. Yeah, that's not accurate, right? So, math clamp. So clamp that value to from 0 to obj collider height. Okay. Then we multiply it by that. Okay. Grip. Okay, great. So, yeah, let's do one here. And also let me undo this. Yo! What up? Yo! It works! Yes! I can't believe it. It works. Look at that. The 2 kilogram object is sinking in water. The 1 kilogram is also sinking, but it's, you know, slightly less. The 3 kilogram one is, you know, completely sunk. This is incredible. Let's make water density 10. So this will make it, yeah, do that. And let's do main Lua over here. Right, so dense crate, let's make that 5. Normal, 10 kilograms. Let's do normal crate 5. Light crate 2. This normal crate will be 5 as well. And go into box and bigger than the city. Let's make that 5. Okay, so here. Ooh, very nice. I like this. So if I compare this with another dense crate, so dense crate that falls on the floor, we'll do 500. Oh, that's not what I want. It's 700, whatever. Now, compare that. Yeah, okay, maybe 10 kilos is a bit too much. Maybe let's do 8. And let's print that at the bottom. Water. This is amazing. This is incredible. This is all you need, my guy. Not all you need, obviously. It should be damping a bit more. But I think, yeah, I think that's really good. I think this is pretty good. Add simple volume underwater calculation. I was gonna do sort of like an axis aligned bounding box and sort of calculate that and find the volume which was submerged in water of the axis aligned bounding box. But right now, because we just have boxes, we don't have like complex polygons, we cannot test this. But to be honest, I don't know what kind of complex polygons I'm gonna need for this game to begin with, you know? So truly, honestly, I believe it kind of doesn't matter at this point. The physics of the water is basically done. Yeah. The water physics is basically done. What we need now is some sort of wave test, basically. Let's see. So what I want is to. So these are the box tests. Okay. It's main Lua. Okay. I'm gonna do so this is just a single configuration of this stuff. Configuration of the world. Okay. So I'm just gonna go ahead and do this. Levels. So let's do levels. for a while. And we're going to do buoyancy equals function, well, it's a level, and load is going to be world talks to the world. Right, we're just going to levels equals require levels. And that's great, right? So I'm just gonna copy this. Oops, I need to do it that way. Okay. I also gotta copy this. Okay. Like that. We'll do levels indexed current level IDX. Load. Just like that. Okay. I'm going to go into levels. Self. Boom. It's going to be 1. Buoyancy. And I'm gonna add level 2. Name C. Oh, waves. Okay. I'm just gonna do this. Let's move these fellas a bit to the right. Okay. And we're gonna have the floor. Let's do 300 on this. Okay. And we're gonna do Wait, I can't throw this stuff? What the hell? Yeah, that's my fault. I should do joint. Let's see. Can I do a spring joint between the mouse? Let's see. Infinitely oscillating spring. No. Like a spring damper connection. Yeah. So what we need is a distance joint, not a revolute joint. Ah. Right. So let's do distance joint. Yeah. So let's do that. So this is going to be body 1, body 2, x1, x2, y1, y2. Right. So the distance, let's see. Oh, damping, frequency, length. This is nice. Okay. Well, I'll do something like this. So first body, second body, first position. Second position should be the same, honestly. Yeah. And this is going to be a distance joint. And then this joint, I'm going to do set. I can set the length. What is the length by default? Let's do set. Well, let's not set length. Let's do set damping ratio. Actually, let's do it without that for now. Okay. Well, it's kind of buggy. Let's do 1. So I can't really throw this thing, can I? Let's do 0.1. Yeah. Let's do joint set length 10 meters. Set length length. Or is that not a function? Yeah, it is. Set length. Alright, let's go. Can't really throw this stuff now, can I? Find it kind of hard. Let's do damping ratio 100. do one sec, I'll answer the call and be right back. All right, we're back. Yeah. We're trying to solve a bug here, right? So the bug is not present right here in this this world, but in this one it is present, which is strange. So water 38. Why are we getting destroyed bodies here? Can we destroy the world? Let's see. So if box to the world, then box to the destroy. Then we create a new one. So, oh, look at that. So when we reset it, the resetting is the thing that does it, basically. Why did this happen? Okay. So let's see. Love to the box to destroy world. Yeah, I think that pretty much solved it. Yeah. We'll do water layer. We're gonna add layers so that stuff that's in water actually shows up as in water. So when we're drawing this stuff, we'll do that. Then we'll do background layer hue. That. Then we'll do that. And we'll do and then we draw okay, now we're going to go into water, and this is going to be layer. Oh, actually, I'll do world debug layer, and this will get drawn. Like there. And I'll do WDBG layer to this. Oh, actually. Actually, it doesn't matter. Okay. And this is gonna be water layer hue. Okay. Might be wise to use canvases instead and then draw them one by one, but we'll see about that. And then we're going to do for the box, it's going to be W debug. Okay, and this is going to be goal layer. So now stuff inside the water stays inside water. It shows up inside water. Right, so now the cursor, right, so water, cursor needs layer to something like that. The 2 kilogram thing should be not so high above the water. Right. So the current situation is like this. We've got buoyancy, we've got water, we've got good collisions, thanks to box 2D. And there we go, yeah. The water is never gonna be like this, ever, basically. So, such an interesting little simulation that's going on here. Anyway, this is a pool of water, and this stuff is just colliding with it. Here's a second test. Different weights of boxes, and they all have different reactions to the water. If it is denser than water, then it will simply sink. Well, actually not exactly, but close to it. Whatever, it doesn't. The exact numbers don't matter. The fact is, we have behavior that looks like buoyancy, and for all intents and purposes, it's gonna, the player is gonna be convinced that this is real and simple to understand buoyancy, right? So you can see the light thing is simply it's way above water compared to the heavier stuff, right? So yeah, and that's the current state of the game right now, and I would say this test was a success. So yeah, so far with rectangles it works. Let's see how it works with how we can get the whale movement to work. But what we also want, basically, oh, look at that, that's so good. Yeah, what we also want is for their next time on the next stream for this game, we're going to be adding waves to it, okay? So that depending on some sine wave, the global sort of force is going to be offset, and all of these things are sort of going to oscillate. And after that, I'm going to add a local sort of chaos to the waves, because if you think about it, when you look at objects in the sky and in the sea, as they move according to the wave, you can see that some of them are sort of still rotating in different directions, and they still have some sort of locality. It's like not all of them are going to be harmonically sort of forming the sine wave. Some of them are going to be slightly offset, okay? And some of them are going to rotate this way or that way. So that's going to be like three-part. First is global waves, second is local oscillations to the waves, and third is going to be local oscillations in terms of rotation, okay? Because if I leave something in the sea, the different parts of water splashing onto it might make it sort of tip over from time to time, okay? So that's what we're going to be adding later. I'm going to put that in the README for this to do. It's going to be global wave system based on sine wave and offset by direction from center. Then I'm going to do local wave system, small noise for each region. This is going to be based on region and not going to be based on individual objects. And so basically Perlin noise, one-dimensional Perlin noise applies to the sine wave. And then we're going to do local rotation wave rotation system, I guess. No, it's a bad. So like apply a rotation I'll do local wave rotation system, yeah, whatever. So rotate objects based on region. So those three things. So the global force, and then the local force, and then local rotation. That's going to give us believable wave physics, I guess. So yeah, this was a success, I'm going to say, and I like it. So let's give it one last look. So we can see, yeah, they're behaving correctly. Now I'm gonna spawn a bunch of boxes here. Yep, looks like water. You know, if you didn't know what you were looking at and you saw this, you would say, yeah, that's water, because that looks like buoyancy. So that's it. All right, that's the end of the stream. Great success for today. So yeah, see you guys in another stream. Right.